For the short introduction, now Professor El-Faqih will be presenting the topics of survival models for breast cancer early interval sensor data via imputation techniques. Professor El-Faqih, are you there?
Yes. Thank you so much for good introduction and for good video. And Assalamu alaikum everybody, and hello everyone. Now I would like to all the friends, everybody there. Let me share screen. Yes, I want to share. Okay. This file.
Professor El-Faqih, can you turn on your webcam?
It's not turned on?
Yeah, it is not on. Sorry.
Okay, hold on.
Professor El-Faqih?
Yeah, you hear me? So I'm trying to.
Yeah. Oh, you're still trying to, okay. But if it's too much of work, you can just proceed if you want to.
Share all from my own. Okay, maybe what I can do, let me just go out and come back again. You can see my slide, is it or no?
Yes. Yeah, we can see it.
But I don't know why I cannot see the video. Okay, can I go out and then come back again?
Oh, yeah, sure.
Okay.
If you wanted to.
Okay, let me.
Okay, it seems that we have a little bit of technical problems from Mr. El-Faqih's computer, so we will wait for him to come back.
Jangan gede-gede, udah kedengeran udah. Nggak mikrofon kan.
So how about it now? Still camera not on? You hear me?
Yes, sir. I can hear you, sir.
You can hear me, okay. But still the video is not on, is it? Or
Yes.
is it? Or here the video is on.
No, sir.
Video, is it on?
No.
Strange, actually. Yeah, strange. Okay, anyway, let me try my presentation first. So it's my presentation as well now. Oh, I think the problem now I know. The camera, yeah.
Okay, Professor Al-Faqih, is there anything that we could help?
I think I identify things that my camera is not working. My camera here in my computer.
Oh,
Yeah.
okay. Do you want to present now or?
Yeah. I think I'm present now better.
Okay, yeah.
Later on, I will solve this camera problem. Yes.
Okay.
Okay, what is my okay, now you can see my presentation. Is it
Yeah.
important?
Yeah, it has started sharing.
You see the presentation, the PowerPoint?
Yes.
The survival model with survival model for breast cancer, part interval sensor, few invitational technique. Okay, so today I'm going to talk about the survival models. I choose a few models, selected model. So we have data from our hospital here and from Hamad Hospital in Doha, and we make this data or simplify this data to be part interval sensor through imputational technique. Okay, so we use some of this imputational technique to get the exact value. Since the participant is not all of them are in survival, so I'm going to give some introduction about what is survival analysis. Survival analysis in general is a collection of statistic procedure for the data analysis for which the outcome variable of interest is time until the event it is occur. As you described just now, you described very well the survival analysis is a statistic method or statistic procedure for analyzing data for which the outcome have to be time until the event it is happen, until that event it is happen. Okay, so since we have time and we have event, so by time we can mean years, we can mean months, we can mean week, we can mean day from the beginning of the study, and we follow up until the event it is happen. Otherwise, I mean, alternatively, time can refer to the age or for individual when and even also it is occur. For example, when we born until we death, for example. Okay, if the event of interest it is a death. Okay, and then what is survival? I think this one we have explained already. So the event, I already explained the time. So what we mean by event, death, recovering from disease, graduation, obtaining job, getting married. So all this is an event. So by event we mean for example, as I highlighted just now, we mean death, disease, incident, relapse from remission, recovered, return to work, or getting a job, graduating from your university, graduating from your school. So the event you are interested with, so that will be the event. So since we have time and we have event, therefore the survival time can be at a more free time, the time from start of the treatment, when we have a treatment, for example, for any of the disease, for example. So to respond, the length of this remission and the time to death. If we are interested, I mean the event of interest, it is a death. Okay, so since we're talking about event, we can have only one event, or we can have more than one event. So although more than one event maybe can be considered in the same analysis, we will assume that only one event is of the our interest in our study. But when we have more than one event, we consider, for example, we have a cancer patient. So the patient died to some other causes than cancer, for example, during operation or infection in the hospital or some other causes, which is that mean we don't identify. So in this situation, we will have more than one event present at the same time. So like we're talking about the recurrence, or we're talking about computing risk, as Dr. Abdul later on, we're going to talk about the computing risk. So that means will be two events present in the same time. For example, like give example of the cancer. So for example, we have an war. For example, the soldiers in a war drive the car to get support to his colleague, so die due to accident. So there's two events present in the same time, as I highlighted also by cancer just now. So that means two events, more than two events. So that means we're talking about recurrence event, or we're talking about the computing risk. I think inshallah Dr. Odus will highlight this in his section. So the time, we mean the survival time, and then the event maybe is the same as a failure. So this is as in engineering, as you explained it just now in your introduction about what we mean by in survival in general. So in survival analysis, we usually refer to the time variable as the survival time. So we refer to the time as the survival time because it is give us the time that an individual has survival over some follow-up of period of time. We also, that means the time, we mean survival time. Even we consider it as a failure because the event of interest usually is death or disease, you getting the disease, or some others negative. Or can be positive. Yes. So when you death is a negative, disease, you get the disease is negative. But when you getting the job, this is positive. So that some other negative or positive individual experience. So that means the failure or the event can be a positive event, but usually we consider it is negative. Usually is negative. So I mean we have a positive event, but it is rare. Okay. So however, the survival time may be the time to return to work after you getting your surgery in hospital, for example. So that we consider as a positive event. Or I said, when you graduate, that is a positive. The event of interest is graduation from the university, graduation from school, or obtaining the job. This is also positive. Okay. So that means the time, we mean survival time. The event we're talking about, we're talking about failure, we can consider that event as a positive or negative event. So in survival data, in survival data, we can include survival time. So in survival data, we have to have our time. We have to have our response to given the treatment, the response for the treatment, and the patient characteristic related to that response, and develop of the disease. So what happened in that disease? So this is all I mean the factor in the survival data. This is the factor in the survival data. Okay, so since we talk about survival data, so that means we have to involve in survival, we have to talk about sensor. So what we mean by sensor? Sensor, there is no survival without sensor. Sensor occur when we have some information about individual survival time, but we do not know exactly the survival time. We do not know exactly what is the survival time. So that means sensor, we have some information. We have some information, but we do not know the exact survival time about the individual. We do not know exact. So for example, I give you an example about sensor. A simple example about sensor, consider the cancer patient. Follow until they go out from the remission. If for a given patient, the study end, let's say we have data for 3 years from the hospital. So, and then our event of interest, it is this. So during 3 years, all the patients, some of them they die during operation, some of them they die without operation, some they die in a home, and 3 years finish, some of the patient is still alive. So we consider that patient alive as the sensor. Okay, so this is a good example about sensor. Okay, so why sensor, or what type of sensor we have? There are general 3 reasons why sensor maybe it is occur. So as I explained just now, a person does not experience the event before the study end. I mean, what I mean, the event the person does not experience event. So I mean that, for example, the patient is not dead until the study finished, 3 years finished. So we consider that as a sensor. A person lost to follow up during the study period. So during 3 years, so one of the patient, maybe we're talking about the data here from Qatar, he traveled to Indonesia and he didn't show up. So there's no record. There's no record in the hospital about him. So disappear. So that means lost to follow up. This is also considered as a sensor. So a person also withdraw from study because of this. If the death is not an event of interest, in this situation, the death is not considered as the event of interest, or withdraw. So, or some other reason, for example, why it is sensor. Okay, so there is main type of sensors. There's main 3 type of sensor, which is right sensor and left sensor and interval sensor. So right sensor occur when the subject leave the study before an event occur, or the study end before the event has occurred. So that's the example I just gave now. It is the right sensor. I mean the study ends, 3 years is finished, but still the patient didn't dead yet, or is not passed away yet. So that means it is considered the right sensor. Left sensor, when the event, and it is most common, I mean right sensor, it is most common use, I mean most use, common use right sensor. Left sensor is when the event of interest has already occurred before enrollment. This is very rare. It is happen. I mean, an interval sensor, we mean that the subject of interest is known only in lie within interval. So that means it is happen within.
Hello.
Hello, yeah, you hear me?
Hello.
You hear me?
Yeah, we can hear you. You can continue.
Okay, good. But unfortunately, my camera is not on. Yeah, so I wearing nice address, but it's not yeah, traditional Indonesian dress, but so that means my camera is not turning on. Yeah, later on I will find out, inshallah, before Dr. Abdul Quddus present, so I can't find out what is the problem is. Okay, so when we study consists of exact data and interval sensor, that means we're talking about part interval sensor. So this is why I'm going to consider for my study today, part interval sensor. Is recently, I mean, many studies have using part interval sensor, and I consider part in my recent research. I think if you talk about last 3 years, all my research have been used. It is partly interval sensor. So that means part interval sensor, it is an interval and exact observation, an exact observation. So that means they have two, according to Kim 2003, according to Azza, according to many authors, using partly interval sensor. Okay, in talking about application in survival analysis, there's so many applications. The survival analysis can be implemented in any field. So survival analysis can use in education. I use for my master student using in education. I use it myself in engineering. I use it in medical, or you can use it in economic. Can use it anywhere, any area. I mean, of study, we can use survival analysis. So that means the application in survival can be implemented anywhere, but most of the application is used in medical, and recently have increased using in industry or engineering. Okay, so this is why I'm highlighting here. So for example, in medical study is used in many cases the life expectancy of the patient after they have starting the event, maybe the event here, they're getting the disease. In education sector, there's so many research use survival analysis to investigate the student retention in education program. Survival analysis used to examine the failure of the machine or the device. This is in industry or engineering. There are so many applications. I mean, it is not only to medical or engineering or education. We can use it in the economic. You can use it in any field. Survival analysis. So that means we can implement survival analysis everywhere. Okay, so we have to have a time and we have to have the event. We have to have the time and we have to have survival time and we have to have the event. Okay, so the main objective of the survival analysis, I mean, we have estimate the time to event what happened for a group of individuals, such as the time until the second heart attack for a group of MI patient, or to compare time to event between two or more groups, such as treat against another treatment, for example, of randomized controls for a trial, to assess the relationship between, I mean, the covariate. So that means what I mean by covariate, for example, when we have survival time, for example, we have the treatment, or we have the age, for example, we consider the age as a covariate. So that means to assess that relationship between the covariate, for example, or the age, for example, or gender, for example, to time to even such as the dose of weight, and etc., as I highlighted now, the covariate. So this is the main objective of the survival analysis. Okay, expect time to event, so which is equal 1 divided by the incident rate. Okay, so since I'm talking about survival analysis, I'm going to talk about part interval sensor. Overall problem, what I'm going to highlight it here for the competition in survival modeling is complicated and and not completely sometimes reasonable on application. For example, when we estimate the barometer of the model, I mean, so that means the competition is not reliable, I mean, or not accurate, if you can say, for estimating the barometer of the model when we have the sensor data. Even though there are many barometric or semi-barometric or non-barometric method. So the main problem here include the computational challenge of estimating procedure or limit to have a flexible method for modeling partly interval sensor data. So we need to have flexible or reasonable or reliable method for estimating the barometer based on partly interval sensor data. So this is the challenge here actually. In generally, most of the previous work related to this area of study will focus on estimating the procedure for the distribution model based on like left interval, right, and sensor. Okay, so in this study, we will modify some method. I think here is a mistake. I'm not of interval. We will modify, yes, this is correct. It is correct. Yeah, in this study, we will modify the method for right and left sensor or interval sensor to make inference about part interval sensor using not only multiple invitational, using some invitational technique on breast cancer. I use multiple invitation, for example, in exponential distribution model, and I use simple invitational for different method. We can see it later. Okay, so the objective here, we need to construct the likelihood function when the data is partly PIC, is partly interval sensor data. And we have to use the maximum likelihood estimation to estimate our barometer. We need to estimate our barometer. We need to find the standard deviation and p-value of that estimator. And we need to compare our method to make sure our method it is reasonable with existing methods such as the semi-barometric Cox model, because semi-barometric Cox model, it is well known and it is there. I mean, it is easy to use using, for example, our software. It is there. Then we investigate and compare our performance with the model, and then we implement the method to real data and the simulation data. So this is the main objective. This is the objective of my research, and that objective of the other objective I highlighted just now, it is for survival in general. Okay, our real data, it is from Al-Amal Hospital. So here is Amal Hospital, National Center for Cancer Care and Research, from National Center for Cancer Care and Research in Qatar here, and it is under Al-Amal Hospital. Amal Hospital under this. So this is a part, Amal Hospital is a part of big hospital. It is Hamad Medical Hospital. We have find this data set. And in this study, all the patients were under observation in Amal Hospital. The data is collected from 1st of February 2016 to 19th of January 2020. I think like a period of 4 years. The data provide detail on 1,008 patients. And we are focusing here on comparing the effect of each treatment. So we have three, if I'm not mistaken, 4 treatment, yes, sorry, 4 treatment for this breast cancer patient. So we need to focus and compare the effect of this each treatment separately on women with early breast cancer. Yeah, in the data we have a few men, but it's not many actually. Among 1,008, so we have like 31, yes, yeah. Okay, so this is some literature review. Use part interval sensor in the analysis. For example, Az and Dr. Noor Ahmed Ibrahim in 2014 used part interval sensor for exponential distribution. But here they use it for testing actually. And Noora, my student in 2018, she used part interval sensor for using Weibull distribution for education data. Kim in 2003 use the maximum load estimation for Cox model he used the cumulative hazard function. And then Zhao and Ziud, my student, also use part interval sensor for medical data as well. He used symbol invitational technique in his paper as well in his thesis. Ziud, he graduated from International Islamic University, and Noura here in 2018, she graduated from Qatar University. Both of them, they use part interval sensor, but with different methodology and different application. Okay, these are some literature review. In 2012, this is Al-Fakim, my name and my colleague. We use Cox model based on expectation maximization for AIDS disease. I think that data we get it from Sudan, and the rest use maximum likelihood estimation based on least square method, and as well for non-barometric estimations such as the Kaplan-Miller estimate. Okay, so this is some literature review. There are a lot of literature review here, but this I highlight this. Okay, for the methodology, I'm using different model. I think I use log logistic distribution with Cox model, and I use AFT and exponential distribution. I think I highlight all these three here. But the challenge here will be, for example, for logistic distribution, in 1972, Cox introduced his model. This is a Cox model. And log logistic for the baseline hazard function. This is H naught here is log logistic hazard function. Then we substitute it here. Then we can have likelihood function. This is general sensor. Delta here, it is general. It is the general sensor. Okay. Then, of course, after we have the likelihood function, then we need to have the log likelihood, and we have to have a derivative. But I think we need to develop this equation to make it part interval sensor. This is just a general sensor, but we need to make it party interval sensor. Okay, so I think I will highlight there. I will highlight it later. So this is like the hazard function, and this is the survival function. Okay, then we get the log likelihood function. Okay, so this is the result from the real data. From so we have, if you can see here, we have our theta. So this is our coefficient, and we have our the delta and lambda. It is the shape and scale barometer, and that is the coefficient. We have the estimation of the coefficient and the shape barometer and the scale barometer, and the confidence interval, and the standard SE is the standard error of estimation, and this is the likelihood ratio test, and this is the B value. Okay, so we have for the treatment, we have radiotherapy. So the patient we treated by radiotherapy, surgery, hormone, and chemotherapy. So we did in this data or in this analysis, we have the covariate as the treatment. For sure, some patients, they have more than treatment. We don't do this yet. We're still doing this. So maybe this will be our next results will be from our side. I mean, so we can see this the result. Of course, we compare this result with the existing. This is the survival function for 2 failure time, we can say, with the treatment and without treatment. So this is with the surgery and without surgery, and here what is radiotherapy and without radiotherapy, with hormone and without hormone, as well with the chemotherapy and without chemotherapy. Okay, So then later on, we move to the simulation based on this log logistic model. So we carry out our simulation study based on real breast cancer data. So we have the estimation from real data, and we check our data, and we find the data is suit for normal distribution. And this why the simulation study is run for 20,000 based on normal distribution with different percentage of exact observation. So for if you still remember about we have to have our exact observation. So when we have zero observations, that means the whole data it is interval. When we have 25%, will be interval, and then 75 exact observation. Then we have 25% with interval sensor. So this is why it become multi-interval sensor. Okay, so that the data we generated based on normal distribution, because we find out when we compare the data with normal and log normal and Weibull and other distribution, we find it's more fitting for normal distribution. So this is why we make our analysis, our simulation, we generate data based on this normal distribution. So when you have normal distribution, we need to have the mean and variance. So the mean will be the estimate of the coefficient, and standard deviation or the variance, we get it also from the real data set. Okay, then to get the exact value with 0% and 25% and 75%, this is why we use the multiple imputation technique. So in this log logistic model, we use a mean imputation technique, and we use a midpoint imputation technique, and then we use a left point imputation technique. Okay, and this is our result. Similar like what? So here you see, when we have exact observation, we have 25 observation, we have 50 observation, and we have 75 observation. What I can highlight here, when we have more exact observation, the result is more reasonable or more reliable. So this is why I said in the problem, we have the challenge of estimation when the data it is a sensor. Okay, you can see clearly here, this is for 75% with the mean imputation technique. This is 50%. So you can see the two failure time are with and without the exactly the same result. So that means when we have highly exact observation, the result will be much better. Or also it depends on the imputation technique. I think we find that the mean is mean and median and random imputation technique is much better compared with left and right imputation. So I think more work have to be done with left imputation technique. And here for other treatment as well. So you can see here, if you can see this graph here, the survival function estimate for left point, you see the left point, there is a difference between the red line and the green light here, as well for the black light line, the survival function here, and the yellow. So it's not exactly the same like what we highlighted early here. You see here, it is the result. It is almost the two curves are almost similar. The two type of failure with treatment and without treatment for using mean imputation technique. And here, when we use left imputation technique, is not exactly the same. They are a little bit different. They are different. They are significant. They are different. Okay. Then the next model it is accelerate failure time model based on Weibull distribution. So this is again same like logistic model. So we use AFT model, but based on Weibull distribution. So this is the model was proposed by Liu and Lim in 2018, and then theta also is the barometers, and delta is the scale barometer. Epsilon here is the error term of the model, and this is the likelihood function. Again, this likelihood function it is for general sensor, is not for part interval sensor. I think I missed to write that, but I will show you later. Okay, ST here is the survival function. This is the survival function, like what I did just now. F of t this is the probability density function. Okay, delta here, when an event has occur, that means it is not sensor. When zero, it is not occur, that means it is sensor. So that means delta here representing either 0 or 1. Okay, so this is the likelihood function, but this is probability density function f of t, and this is a survival function. Later on, we have to substitute both functions based on a of t model with Weibull distribution, and then we got the log likelihood, and then we use a numerical method or maximum to estimate the barometer using the model. And here it is the result based on the survival function for the treatment. This is from the real data. I think here I compare this is with Cox model, semi-barometric Cox model, our AFT with Weibull distribution, and with the Cox model with treatment and without treatment, because we have two types of failures. So that means the both the result is comparable, so that means can be acceptable comparing with semi-barometric Cox model. So this is why we go for another treatment as well, for RT and then for surgery as well. This is the two here. The first two, it is for chemotherapy and for hormone, and here it is for surgery and radiotherapy. Okay, comparing the model with Cox model. So this is the result from the simulation study. You can see here when we have right imputational with 0 exact, so the two lines are different. I mean the two failure time are different. For 25 with the right point imputational technique also it is different. But if you increase the percentage of exact value, so you can see here when we have 75%, so the result it is more accurate here, and here it is 450 if you compare it with 0 and 25 using right point. But I think if we use midpoint or median point or random or multiple imputation, will be much better. Okay. Then the last model I'm going to use here, it is exponential distribution. So this is exponential distribution model. So we have beta naught, we have beta, and we have beta naught indicates the interception, and beta representing the regression coefficient, and Z here is the covariate. And this is again, it is the likelihood function, the general likelihood function. Ft, it is the probability density function. St, it is the survival function. And as we highlight just now, delta, it is either 0 or 1. 0, it is sensor. 1, it is the event, it is happen. So this is the general equation after we substitute AFT and survival function, and then we go the log likelihood, and we have substitute the exponential distribution, and later on we have to find the derivative, make it equal to 0, use the maximum log estimation to estimate the parameters. So here we use the Newton-Raphson method for estimating all our barometer. Okay, then multiple imputation is much better, is a little bit complicated with simple imputation. Simple imputation, we mean like right, midpoint, mean, and left point, a random point. This is all simple imputation. But what we call it, multiple imputation, it is attractive method for handling missing or imputing the exact value. The idea is proposed by Rabin in 1977. So we have to impute the exact observation by using appropriate model with incorporate random variation, and then we have to perform the desired analysis for the data by using a standard and complete data method to average the value of the barometer estimate across the invitational value sample in order to obtain the single point at the exact observation, and to calculate the standard error by averaging the square standard error of the imputed value of the estimation. So it is a little bit complicated in R when you do it, but it is have a better result for sure. Yeah, and this is our result from exponential distribution. We compare it with Cox model. So you can see the estimation, it is a little bit different, but it is comparable between for all these three treatment with based on the standard error. Yeah, I think the result it is comparable, so can be acceptable from real data set. And here the survival function from semi-barometric Cox model with exponential model. So it is as well, it is comparable. And here for hormone treatment, and here for chemotherapy treatment, and this is hormone treatment. And here for radiotherapy treatment, it is almost the two survival curve, it is equal. Okay, and here the three treatment we comparing. So RT radiotherapy look have a longer survival compared with others treatment. We are really not interested here for which treatment is better and use. Only we find out using the treatment, the patient have a longer survival comparing with not using treatment. Okay, so this is from simulation data. From the simulation data for exponential distribution, again with a different percentage of exact observation. So the result here based on multiple invitational, even though with lower percentage of exact, it is more suitable and more good compared with simple invitational technique. So we recommend this actually. So we can see here, even for 0, for 25%, both failure time are the same. So when we compare in this exponential distribution, invitational technique with left invitational, so just for better clarification, to see how multiple invitation is functioning well compared with left invitational or no. So this is the result. You can see it clear here. When we use a left invitational, multiple invitation is much better. We get better result. You can see here in figure 9 and figure 10. If you compare it with the figure just now, if you compare it with figure 5, figure 6, so it is much better using multiple invitational compared with left invitational. So we just for clarification. Yeah, I don't know where the red color this come from. Okay, so now we move to the last point, which is the conclusion. Overall, the result of a study using survival curve has showing the 4 treatment is not 3 treatment provides a patient with a long survival. Yeah, as I highlight now, we are not comparing the treatment. I'm comparing when used the treatment. I'm not using the treatment. So the patient using the treatment have a long survival compared with those they don't use the treatment yet. We conclude that both results from simulation and real data are suitable for both intervals. So this is our main attention here. So we need to have a reliable or flexible model based on Barth interval sensor. Then finally, the results observe that when observation in the data are more exact, when you have more exact like 50, 75, the model is better fit. The model is better fit, which is similar inference of the researcher like Ziyud in 2016, Al-Harbi, and other researcher, which is I don't write it here. Okay, suggestion for future research is still when we have I mean, lower exact observation, and we need to look at it again. And then here in this research, we focus on the treatment on the data set. So maybe we can extend to look the relationship between the treatment and age and gender, level of education, so that we can make the result is more good actually. And then multiple petition, we find it is good. So comparing with left petitioner, so maybe we have to look why left petition is not good. I mean, the result have to be improved. Yeah. And then in terms of using multiple petition, how to compare it with expectation maximization logarithm to see the results. These are some reference. Yeah, I use it here in the analysis. So I hope my voice, my presentation was understandable. I'm sure for not all the participants. MashaAllah, the participant is 200, more than 260. So I'm done with my presentation. Thank you for listening to me. And if there's any question or any comment you want to highlight to me, will be good.
Yeah, thank you so much, Mr. El-Faqih, for the presentations. And now we are moving to the discussion session. We already have some questions in the chat. So later on, you can see it on the screen. And before it shows up, I will. Okay, I will collect it. Okay, there is a question from Dr. Mir Rauf Ahmad from Amar Singh College, Cluster University, Srinagar. He asked about which data imputation is better, central tendency based or regression based. Thanks. You can answer.
Okay, thank you. Okay, so which data imputation is better, central tendency based or regression based? I think in this research we haven't used because we use a regression, so we don't use the central tendency based. So we're not comparing this, but in terms of imputational technique, we find multiple imputation is more suitable compared with a simple imputational. So this I can just answer to that, Doctor. So Dr. Rauf, are you here with us? If you have any other comment related to my answer.
Okay, Dr. Mir Rauf Ahmad, are you here?
Yeah, we can have a discussion, no problem.
Yeah. Dr. Mir? Okay. Dr. Mir, is the explanations is already enough for you? Okay. Okay, he's not responding, so I guess
it's okay, no problem. We still later on I'm around. We still have questions. It's okay, even after Dr. Abdulwadud's presentation.
Okay, yeah, and then there are another questions from Liza Kurniasari from Polstat STIS. Can we use numeric data as predictor variable?
What is STIS?
STIS is one of the institutions of statistics in Indonesia. So it's a university.
Okay.
In statistics, specialty in
and
statistics.
We use a numerical data as a predicted variable. Numerical, you mean prediction variable? Yes, I think we can use, yes. Yeah.
Okay.
Yeah, we can use the numerical data. Yeah.
Okay. Miss Liza? Miss Liza, are you there?
Yes, Miss.
Oh, yeah. Is it already enough, the explanation, or you wanted to ask more? Mau ditambah lagi, Bu?
Usually, usually I know to
Boleh pakai bahasa Indonesia, Bu? Kalau susah.
people only okay.
Ya.
Sorry, karena biasanya saya lihatnya hanya pakai data kategorik gitu kan. Ternyata bisa ya untuk numerik. Make sure.
Okay. Miss Lisa said that usually she only see the survival analysis with categoric variable. So yeah, it's
Can use a numerical, yes. Can use a numerical, yes. Thank you, Sister Lisa. Thank you. Now you can see I think I just need to switch on the camera, you see?
Yeah, it's so visible now. I can see your nice dress.
Thank you.
Okay.
After the presentation, yeah.
Yeah. And then there are another question from Yaya Setiadi, from the same institution of Miss Liza. Oh, SCIS is College of Statistical Sciences. Okay.
Oh.
Yeah, in Indonesia. So Mr. Yaya asked, when can we use the survival analysis? And then the second question, is there any requirements for event and sensor in a research in order to get estimation of the parameters to be not biased?
Okay, good. So you remember in our introduction, we have highlighted the survival analysis. So we need a time. So that means we have to have a survival time and we have to have event of interest. Yeah, we have to have these two. If we have these two, then we can implement survival analysis. Otherwise, no.
Okay.
Yeah, we have to have an event of interest. So maybe the event of interest is the graduation, is getting married, getting a job. So let's say you graduate during 4 years. Some students graduate earlier than 4 years, so maybe they are good. They can take more courses. They can graduate early. So the graduation time, that's the event. So during 4 years, if no one graduates, that will be considered as a sensor. So we can implement the survival analysis. So that means we have to have time and we have to have an event. If we have these two, we can implement everywhere. Sure.
Okay. And another one from Mr. Yaya as well. The survival analysis is similar to regression analysis. Is there any assumption that need to be done? Or if not, what are the consequences?
Yeah, if you talk about yeah, I didn't highlight this. I think I skipped it yesterday in my note, because when we can use survival, when we don't use survival and statistic. For example, why we don't use, for example, if I want to compare the treatment, I can use t-test or I can use any other regression. Okay, but we have event and we have time, so this is why we can implement survival. Yeah, that's the simple answer is.
Yeah. Okay. Mr. Yaya, do you want to elaborate more or do you want to discuss?
Ya, terima kasih atas jawabannya, Prof.
Yeah. Okay.
Yang ingin saya tanyakan adalah apakah harus semua asumsi OLS itu terpenuhi atau cukup salah satu atau dua mungkin gitu ya, nggak harus keempatnya begitu. Dan kemudian kalau misalnya tidak terpenuhi keempatnya, apakah bisa diteruskan analisis survival ini atau kita harus menggunakan analisis regresi yang lain? Dan yang paling ingin saya ketahui begini, Bu Marisa, proporsi antara event dan sensor itu yang idealnya berapa? Karena kalau eventnya terlalu kecil, itu kan bisa bias nanti estimasi parameternya. Terima kasih.
Oke, Pak, ini event atau time seriesnya? Maksudnya eventnya aja kan, cuma maksudnya
ya, eventnya kan ada yang rare cases, Ibu ya. Kalau rare cases kan kita bisa pakai regresi yang lain ya, Poisson atau hipergeometrik atau negatif binomial dan sebagainya. Nah, apakah kalau rare cases itu untuk event bisa terus digunakan survival analysis atau tidak? Nah, jadi pertanyaan saya, idealnya bagaimana proporsi antara event dan sensor? Terima kasih.
Okay. Okay, so it's quite a long, a long
No problem.
discussion.
Yeah, it's okay. It's okay.
Yeah, I will
It's the research. You
translate.
have to. We will learn from that as well, actually.
Yeah. So
It's learning process.
yeah. Mr. Yaya asked, does it need any OLS assumptions? And are the event need to be proportional with the sensor? Because there are some cases in rare cases like that. So what is the ideal proportion for event and sensor? That is what he asking.
Yeah, actually, this is deep question. Yes. Yeah, I think what he talking about assumption of Cox model. I mean, yeah, there is assumption for sure. There is an assumption we have to follow. We have to follow up with for example, when we implement any model in the survival analysis, generally, for example, Cox model. So we have to have an assumption to use a model. Yes, we cannot just simply use a model for survival. Yeah, we have to have that assumption. I think he is right. I understand. I think in Indonesian language what he's trying to say. Yes. Yeah, he's right.
Yeah. Okay. So you need an OLS assumption to be.
Yeah, we need,
okay.
And we need also to check the model assumption. Actually, which I don't do also in my presentation. I didn't check the assumption of the model. Is it fulfilled or not? He is right. Yes, I am agree with him. Yeah, but we did it in the thesis actually. But my presentation will be quite long if I did all. Yeah.
Yes, that will be another paper.
Yeah, it will be long. Yeah, actually, what I present today is from my student. It's my student. Yeah, it is my student research.
Okay. I see. Okay, I will try to explain it to Mr. Yaya. Mr. Yaya, do you catch all of them, the answers?
Okay. Jadi OLS harus terpenuhi semuanya. Sedangkan yang rare cases itu mungkin itu ya relatif ya. Tidak ada ketentuan yang pasti begitu kira-kira ya untuk proporsinya.
Okay.
Okay, thank you, Prof.
Thank you for your attending. Thank you so much.
Thank you so much, Professor.
Terima kasih banyak.
Terima kasih.
Thank you so much. And okay, there are another question from Dr. Danesh Kumar from Manon Manayam Sundaranaar University, Tirunelveli, India. So how to compare two or more survival curves? That is
okay.
The question.
Is a good question. If you see all my curve here, we have the survival graph. So to compare the treatment, so we consider the patient given treatment and patient without treatment. We want to see which one have a long survival. So if those who get the treatment have a long survival or not. So most of the results show that most of the patients who given the treatment have a long survival. But in terms of comparison, so we find actually in one of our student research, I think using the exponential distribution, chemotherapy is much better. I mean, have a long survival compared with other treatment, yes, for sure. And which is we don't do yet in our research. Of course, there's some patient did chemotherapy and surgery, so we don't mix this two. So we did individual. So the survival curve we have to be two curves, one representing the treatment and the other one not treatment. We have to have this two failure time. So one is treatment, the other one without treatment. So we want to see which one have a long survival. Is it this why we can justify to the hospital that you better use this treatment, because this treatment, when you give it to the patient, they have a long survival. So yeah, it's a good question.
Okay. Do you Do you have any questions, or is it enough for you, Dr. Dinesh Kumar?
Yes, madam. Yes, madam. Thank you.
Okay.
Thank you, sir.
Thank you.
Thank you, brother. Thank you. Thank you, doctor.
Okay, there are another question from Muhammad Fatkur Rahman from Universitas Jember University. Why do you use partly interval censored data, not right censored, left censored, interval case 1, interval censored case 2 for case of breast cancer? Thanks.
Yeah, okay. It's a good question. Yeah, we use part interval because still the research ongoing on part interval, and researchers have used a lot for left sensor, right sensor. So we want to have a challenge actually to see whether part interval sensor is can be functioning or working well or not. Because in left sensor, several researchers, left sensor, right sensor, interval sensor, several researchers have been used. So we want to address part interval sensor, and the challenge here, we have to use the imputation technique to obtain the exact value, because in part interval sensor, maybe the data it is already interval, so we have to create the exact value using midpoint, using left point, using mean imputational, using multiple imputation. So we need to have the challenge. So this is why we use a part interval using imputation. Yeah.
Okay. Mr. Fatkur Rahman, are you there? Is it enough for your question?
Enough. Thank you.
Okay, thank you.
Thank you for your question. Thank you. Thank you, brother.
Yeah, I think that's all the questions for today. Yeah, thank you, Professor Al-Fakih, for answering the questions. So I will provide some highlights from Professor Al-Fakih's presentation. So survival analysis actually can be used for one or more than one event. Time means the survival time, and for event, usually it is negative, like death. It can be positive as well, such as getting a job. And then for survival time, the example is time to return to work after a surgical procedure. And for the censored data, it means that we know only some information about the survival time, not the exact survival time. For example, patients in remissions will be studied, but if they are out of remission, the study will stop. And then 3 reasons why censored data exists is the sample do not experience event, and the person lost follow-up during the study, and the person withdraw from study because death or other reasons. And there are 4 treatments that Mr. Al-Fakih studied, which is radiotherapy, surgery, hormone, and chemotherapy. And then he compared the survival time between with or without the treatment. And I think that's all the highlights. I'm sorry because I will not go deep into the theory because yeah, because I might be
your
wrong.
Background is it statistics or what? You are a statistician?
Yeah. My background is statistics, but I'm not really familiar with survival analysis as well. That's why I gained a lot of knowledge from here about your presentation. So I knew.
Yeah, you have Dr. Abdullah there, so you can do a lot of research with him. Yes, yeah.
Yeah, I hope so. Thank you.
Good. Yeah. Thank you.
Yeah, thank you so much. Okay, I think that is enough from Professor Al-Fakih. And then now we are moving to the second speaker, Mr. Abdul Qudus, PhD. So Mr. Abdul Qudus is the Dean of Faculty of Mathematics and Natural Sciences, Universitas Islam Bandung. He had his PhD in statistics from University Putra Malaysia in 2009. Before, he was the head of research division at Research Management and Community Services in 2018 until 2020 at Universitas Islam Bandung. As a lecturer in Department of Statistics, he has done many research, especially in the field of statistics, computational statistics, statistical modeling, survival analysis, and his research interest is in statistical modeling of various application fields such as health, economic, and education. Okay, that's all for the short introduction. Now, Mr. Abdul Kudus will be presenting the topics of regression trees for sub-distribution of accompanying risk. Mr. Kudus, the time is yours.
Okay, thank you, Mr. Chairman. I share my screen. Okay, can you see my share screen?
Yeah, we can see it.
Okay, Bismillahirrahmanirrahim. Allahumma sholli ala Muhammad wa ala ali Muhammad. Rabbi israh li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Assalamualaikum warahmatullahi wabarakatuh. And good afternoon, everyone. Thank you to the committee for inviting me to the joint webinar and giving me the opportunity to talk about my research. And thank you to Dr. Faiz for being my partner in this webinar. Actually, we are long time ago as PhD student in UPM. Okay, the subject of my talk is regression trees for sub-distribution of a competing risk. Before I begin, let me introduce myself. I'm Abdul Kudus, and I'm from Department of Statistics, Bandung Islamic University. And here's for correspondence, I have my email address here and my Twitter ID. Okay. Today's presentation is about the extension of regression tree method to cope or to handle competing risk survival time data. This topic is in the field of statistical modeling, particularly by using statistical learning. Here we use regression tree method. And here's the overview of the presentation. The abstract. Studies with multiple endpoints are common. In such cases, the endpoint consists of several distinct events of interest, and the eventual failure being attributed to one exclusively to the others, which define a competing risk situation. And one observed for each subject simply a fail time and a cause of failure. So here in competing risk, we observe a fail time. This is random variable, time random variable, and also the cause of failure. Not only the censored indicator, but also the cause of failure, because in competing risk setting, we can have more than one event. And one of the method to describe the competing risk survival time data is sub-distribution function. Okay, this is the primary measurement summarizing the likelihood of a specific event. And this sub-distribution function will develop for each event. Let's say we have three type of event, so that we can develop three sub-distribution function. And then we go further for the regression setting. Here we analyze the relationship between the outcome. Our outcome here is competing risk survival time. And for the regression setting, we have also the covariate or covariable or our independent variable or predictor. And for the regression methodology, we use some kind of statistical learning, which is a tree-structured regression. Okay, because why? Because we want to extract a meaningful subgroup of subject. Yeah, if have many patients, we want to know is there any subgroup of the patient. And here we develop the regression trees based on deviance statistics, and so many ways to develop the regression tree, and still many researchers still do on it up to now. And in the last part, the application of method to there are two cases. The first one is for breast cancer, and the second one is for contraceptive discontinuation data. In both two applications, we want to identify the small group of women that have a similar characteristic of competing risk survival time data. Okay, this is the introduction. For the outline, the first one is introduction and then competing risk. The first part is on competing risk regression trees. This is the main part. And the fourth section is on the application, and finally we come to conclusion. Okay, actually the title of my presentation contains 3 keywords. We have 3 keywords. The first one is regression tree. Okay, and all the keywords here are very specific terminology in statistical science. So maybe for some attendants who has no background in statistics, maybe I have to explain it slowly. Okay, the first one is, what is regression tree? Regression tree is some kind of regression concerning the relationship between Y, this is the dependent variable or response variable, and our predictor X. Okay. And the second one, the keyword is subdistribution. Subdistribution is some kind of data summary, particularly for summarizing the competing risk survival time data. And the third one is competing risk. This is a special kind of survival data. Professor Faiz has explained the terminology of survival data. Okay, there are special features of survival data. The first one is survival time data commonly is strictly non-negative observation. Non-negative, maybe 0, but usually a positive value. The second one is rarely normally distributed, but right skew distribution. So we cannot use the ordinary regression method to model the survival time data because rarely normally distributed. And the third one may be incompletely determined for some subject, what we call as sensor data. So this is the 3 special features of survival data. What we have to be concerned with in order to do analysis well. Okay, I have to I want to explain the censoring in detail. There are one kind of censoring which we call right censoring. Right censoring is when the event time is larger than the censoring time. Let's say this is the leukemia patient in remission. So here the point of study start. But the researcher stopped the observation here, but this person still does not experience the event. So this person is called as right censored. Okay. The second one is left censoring. When the event time is smaller than the censoring time. Okay, let's say a study start here. Let's say for the case of COVID-19 infection. Let's say this is the beginning time of what we call COVID-19 exposure. And we know that if we are following person until they become COVID-19 positive, we may record a failure when a subject first PCR test positive here. We can record the failure here, but we know that we do not know exactly the time of first exposure, maybe here, and therefore do not know exactly when the failure occurred. Thus, the survival time is censored on the left side, since the true survival time, which is from here to here, which end at exposure, is shorter than the follow-up time when we record here. This is the type of left censoring. And the third one is interval censoring, when the event time is only known to fall in an interval. Yeah, frequently happen when we have periodic follow-up. Let's say we instruct here at 8 months, and we observe here at 10 months, and maybe between 8 and 10 months, the person or the patient is experience the event. So here we can classify as interval censoring. And next we will go further for the competing risk methodology. Okay, in the previous part, all the events were treated as identical. Yeah. Let's say all deaths were the same, but it is essential to distinguish the different kind of event. So we want to distinguish the different kind of event here. For example, to evaluate the efficacy of heart transplants, we want to treat death due to heart failure differently from death due to accident or cancer. So competing risk method is for handling this kind of situation. So the main point for the competing risk is we have to distinguish different kind of event. We cannot treat it as identical, all identical. Okay. Consider survival time data where each subject may fail due to one of so many cases. Yeah. Let's say of J, where J is greater than or equal to 2 causes. Occurrence of one event preclude observation of the other event on the same individual. It assumes that a patient can fail only from the one cause. Survival time data is defined specifically as competing risk. And for n subject, we observe a pair of random variable, t and delta, where t is on study time, and delta is indicator of the cause of removal from the study. So t is length of time to the event occur, and delta is the type of event, the type of event. So delta will be equal to 0 if the ith patient was censored, and delta is equal to j if the ith patient was failed from cause j, where j is equal to 1, 2, up to capital J here. If we have J classification of event. Okay, the objective of computing risk data analysis is to isolate the effect of a given risk or subject of risk acting on a population. So here this is the extension of survival data. For example, woman who undergone breast conserving surgery was followed until relapse. So let's say here, this is the start of treatment, and we follow up to maybe relapse or second malignancy or death or censored. So in this kind of research, we have to use computing risk methodology. Okay. The second example is, let's say, from the database of Indonesian Demographic Health Survey, we observe the length of time. Okay. We observe the length of time from start of contraceptive use, yeah, up to 3 type of event. The first one is maybe she used the contraceptive, but in the end become pregnant. It we call as failure of the contraceptive method. The second type is she used the contraceptive method and then she stopped to use the contraceptive method. Then the discontinuation type for the second case is what we call abandoning. Okay, and the third one is, let's say she used first J method, and then she replaced to the other method, let's say the K method, where J is not equal to K. And in this setting, in this case, we call as switching. So from the start of use, maybe failure, the contraceptive method is failure. This is the length of discontinuation, but in the end, maybe failure or abandoning or switching or censored if she still use the contraceptive method. Okay, in the second example also, we have to use the methodology of computing risk. Okay, as I said before, the one method to summarize the computing risk data is what we call subdistribution function. It depends as this function. This is the probability of t less than t for particular type of event. Yeah, let's say we want to estimate f1t. This is the probability of stop. Yeah, the probability of stop. The probability of not use, let's say not use the contraceptive method anymore. when the particular type of event is equal to 1. And we have to use, and we have to estimate up to J. So here J is equal to 1, 2, up to capital J. Okay, this is defined as the probability that an event of that type occurs at time point between baseline and time t. Let's say this is the baseline and t. What is the probability that an event of that type occurs within this length of time? So subdistribution function is one method to summarize the competing risk survival time data. Okay, if the data do not contain any censored individual, subdistribution at time t can be estimated as the ratio of the number of subjects who experience that event type until time t divided by the total number of subjects in the data set. Okay, as time increases, the subdistribution increases from 0 to the total proportion of event. So the curve should be like this. Okay, this is T, and this is subdistribution function of type of event J here. If the dataset contains censored observation, which is not all the subjects are observed to experience an event, the simple estimate must be modified to correctly account for censoring. And this is commonly we face in the research. Okay. And then if beside response variable or survival competing risk survival time data, if we have also covariate, let's say X1, X2, and so on, and then we want to use the regression model. Okay. One type of the regression model for competing risk survival time data, what we call as direct subdistribution regression model. This is the model. Yeah, this is the model where G here is log-log transformation. Okay, if we re-express the model number two into another quantity, let's say what we call subdistribution hazard, then this would be like this. So this is comparable to Koch regression. Okay, in the regression model 3, we use the subdistribution hazard model to model the competing risk survival time data between T. Oh, here we use another notation Z1, Z2, until Z3. And this is actually the subdistribution hazard function. So our regression is based on this quantity. This is the rate of failure due to type of event J, given that the patient is still alive. This is the condition. The patient is still alive, or he dead due to another cause of failure, not the J cause of failure. So this is the another quantity for competing risk survival time data, which we call as subdistribution hazard function. And we extend the direct subdistribution regression model to competing risk regression trees. Okay, here we take another regression methodology from statistical learning, what we call regression trees. Because the regression method, as we know, model the relationship between predictor X, X or Z, and computing risk survival time outcome. Here we use T and delta. And another one, with regression trees, we want to identify which risk factor significant for an outcome. Our outcome is computing risk survival time data. And then in regression trees, we also want to compare the group of subjects after adjusting for factors. Okay, when we develop the regression tree for computing risk survival time data, we use the subdistribution hazard regression model based on cut point for particular predictor variable. Let's say Z here, in particular cutoff point, let's say gamma here. And we want to know which point for gamma here. This kind, which point to gamma here. And for this kind of problem, we can use the regression tree methodology. And this model is estimated by using partial likelihood function. Okay, and then we get the deviance, which is -2 times log likelihood of the model, of the estimated model. And we use this deviance as splitting function for the regression trees methodology. So we can see which kind of gamma, which is the best one with the smaller value of deviance here. Okay, this is the algorithm from regression tree which we adopt for this kind of computing risk survival time regression. Okay, here let's say we have predictor variable Z, and we want to know what is the cut point gamma here. Okay, if Z is ordered covariate, then we want to split into two groups. The first one is a group of ZK less than gamma, and the second one is for the others. But for nominal, if Z is nominal, if the predictor is nominal variable, then we have to develop any subset of possible nominal value. And then we will come up with the best split, which is corresponding to the minimum deviance statistic. Okay. After we get the best split, and the data will be divided into two groups, and we do this recursively to the sample until stopping rule is met, and we will develop a large tree, what we call is gamma zero here. Okay, this is the algorithm for the regression tree for computing risk survival time data. Okay, next, the first application. For the first application is for the breast cancer patient. We have a research from another researcher with 639 women with this inclusion criteria. And then those women were randomly assigned to receive. The first one is tamoxifen plus breast irradiation. So this is the first treatment, or another one, which is only treated by tamoxifen alone. For the first group, there are 319 women, and for the second one group, there are 320 women. And there were several events that might occur following the treatment after breast conserving surgery, namely maybe relapse, maybe second malignancy, maybe death, or maybe censored. So here the one example of computing risk survival time data. This is the detail of our variable. The first one is Tx, which is treatment, 0 for tamoxifen only, and 1 for radiation plus tamoxifen treatment. And we have also another predictor variable, which is the PET size, the size of the tumor, and histology, must be ductal, labora, and so on, and hormone receptor level, hemoglobin, and so on and so forth. And this is our response variable, our computing risk survival time variable as a response variable. This is the time from randomization to event, maybe relapse, second malignancy, or death, or maybe a censored. Okay, and we also observe the status of last follow-up. Yeah. The status, the indicator of the last follow-up. 0 for censored, 1 for relapse, 2 for malignancy, and 3 for death. So this is the example 1, the first example for computing risk survival time, computing risk regression. Okay. Before we analyze by using computing risk regression trees, we describe the data for each group, okay, in terms of subdistribution function. In terms of subdistribution function. So this is F0, mean for the tamoxifen only, and this is F1 for this is the subdistribution function. This is for the probability of relapse, only for relapse. As we know that we have 3 kind of event, relapse, malignancy, and death, but we concern here for the first type of event, which is relapse. We can see here that for those patients were treated by tamoxifen plus radiation, the probability of relapse is lower than the group of patients which treated by tamoxifen only. So this means that the second one, which is tamoxifen plus radiation treatment, is better. It's better. Next, we want to know, is there any subgroup of the data? So here we conduct a 2 separated regression tree for each treatment. The first one is for tamoxifen group, and we will come up with the 1, 2, 3, 4 group here. 4 group. This is the result from computing risk regression trees. The first group is node number 2 here, which is the patient with tumor size less than 1.3 centimeters. Okay, this is the group of patient with tamoxifen treatment with characteristic tumor size less than 1.3 centimeter. Let's say a small tumor size. Okay, And then the second one is node number 4 with this characteristic with tumor size greater than 1.3 centimeter and age less than 59.5 years, and so on. We have 4 subgroup of data. And for the second group, for the second treatment, by using the competing risk regression trees, we will come up with 3 subgroup of patients. This is the result from competing risk regression trees. The first subgroup is node number 2, which is the patient with tumor size less than 2 centimeters. Okay, and the second subgroup is the patient with tumor size greater than 2. So we go to the right, means tumor size less than 2 centimeter is no. It means that tumor size greater than 2 centimeter. Okay, and hormone receptor level is negative. So here the hormone receptor level is negative. So we have 3 subgroup of patients with tamoxifen and radiation treatment. And then we inspect the subdistribution function for all the groups, Yeah. The blue line, this is the blue line, 1, 2, 3. This is for the radiation and tamoxifen. For the red line, this is the subgroup from the tamoxifen only treatment. What we can see here, the blue line, this is the this is the poorest patient. Why? Because the probability of relapse is the big one. Okay, and this is the best subgroup. We can see here that the poorest group and the best group come from combination of radiation and tamoxifen. So the first insight here that the tamoxifen plus radiation will lower than the tamoxifen only is not always lower. It's not always lower when we separate between here. The first one, the poorest subgroup is with tumor size greater than 2 and hormone receptor level is negative. So for the group of patients with the big tumor size and the hormone receptor level negative, the treatment of radiation and tamoxifen will be worse than the patient here. But yes, for the patient with combination of treatment and tumor size is small, the probability of relapse is still good here. So this is the result from competing risk survival time regression. We can separate from the big group here, only 2 group, into detail here. Okay. Yeah, overall comparison for both treatment reveal that the poorest and best prognosis are from tamoxifen plus radiation treatment group. So the The poorest and the best one is in blue group. In blue group. We found that tamoxifen plus radiation is not effective for those women whose tumor size greater than 2 centimeter and negative hormone receptor level. This group is more likely to relapse compared to the others. This group here. On the other hand, patients with tamoxifen plus radiation and tumor size less than 2 centimeter have the best prognosis because they are less likely to relapse. This is the bottom line here. The analysis for two other events, which is second malignancy and death, show different results. This show that patients give the different response to the treatment. So this is the first application. And the second application is for the contraceptive discontinuation data. We have 2,361 women from Indonesian Demographic Health Survey. We observe the time of the last contraception use. So this is the last contraception use. Okay, we observe from the start here up to the event. The event may be failure, maybe abandoned, maybe switching, or maybe censored if still in use. And we have 6 predictor variables here: age, socioeconomic, resident, religion, education, and contraceptive method. And this is the result. This is for failure event. For the first type of event, we have 4 subgroup here. We have 4 subgroup here. The first one here, node number 7 here. Node number 7 is a woman whose age between 34 and 29, and he not use IUD or implant method. So for those women whose age between 29 up to 34 and which not use IUD or implant, for those group will be the first one. The probability of failure is the biggest one. And the best one is node number 3. Node number 3 is here, the group of women which age greater than 34. Okay, this is for the failure type of event, and this is for the abandonment type of event. We only have 2 subgroup. The good one is the better one is node number 3, which is age greater than. This is age greater than 38. Okay, and and the other, this is node number 2. And then the third type of event is switching. The best one is node number 5 here. Node number 5 is woman whose age less than 38 and the education is university. So maybe for those group of women, the probability to switch is the best one. For those women, maybe have literation in using different kind of method of contraception. Okay, And finally, the conclusion, the competing RIS3 method intend to provide exploratory data analysis. And we have applied for the breast cancer data, and so the method could identify the group of data which had similar response to treatment. And the method works well also for contraceptive discontinuation data. Okay, thank you.
Okay, thank you very much, Mr. Abdul Kudus. And now we're moving to the discussion session. Oh, before the discussion, we will have a photo session before probably some of you are busy. So yeah, we are gonna do the photo session before the discussion. Can you turn on the camera?
All right.
Okay. Yep. Ibu Miski, are you ready?
Yes, okay. There are several slides here, so please stay cheese until I say finish. Slide 1, 1, 2, 3. All right. Slide 2. 1, 2, 3. Slide 3. Okay, 1, 2, 3. Slide 4. 1, 2, 3. Slide 5. Please wait. 1, 2, 3. Slide 6. 1, 2, 3. And slide 8. 1, 2, 3. Okay, the last slide. 1, 2, 3. All right. Thank you.
Okay, thank you, Miss Miski. Okay, now we're moving to the discussion session. Okay, there is someone who raised their hand. The first one is Miss Suparti. Miss Suparti, are you there? Hello? Okay, she's not responding. Or Mr. Abrian? Hello, Mr. Abrian? Do you want to ask some questions? Oh, no? Okay. Okay. Okay, I have questions actually for Mr. Abdul Kudus. For the breast cancer model, do you also modeling for another status like malignancy or death? And the second question is, can we use other modeling than regression trees for in the survival analysis? Thank you. I think you can answer now.
Okay, thank you. I will share screen again regarding to those questions. Okay, here. Actually, I just saw the first type of event, which is the the failure, which is the relapse, yeah. But we have another two type of event, which is second malignancy and death. And of course, we develop the model 2 for the second and third type of event. And I explained here in the last paragraph, the analysis for the two other events, which is second malignancy and the death, show different results. I mean that the classification of the subgroup is not the same with this first type of event. Okay. As we can see here that the classification of the subgroup first based on tumor size, and then based on age, and the third based on hemoglobin. But for the second and third type of event, the result is different. But the main point here that our result show that patient give the different response to the treatment. This is the result of the research. Okay, for the second question, can we use the regression trees for survival time data? Of course. Actually, our method is go beyond. We direct go to competing risk survival time data. And of course, the research start from the use of regression trees for survival time data, which is treat all the event as identical. Okay, the development of the method firstly use regression trees for the common for the ordinary survival time data, and then it extend for the competing risk survival time data. Thank you.
Okay. And can you actually, this one for the conclusion, you use the regression trees, right? But other than regression trees, can you use other methods of classifications in the survival analysis, such as clustering or classification?
Yes, of course. Okay. So many ideas to adopt method from statistical learning, from machine learning. Let's say neural network or support vector machine for analyzing the survival time data and competing risk survival time data. Okay, here we adopt the machine learning method, which is regression trees. Thank you.
Oh, okay. Thank you very much. Yep. I think, are there any questions from you, from the participants? Yeah, I think that's all the questions that we have for today. Okay, now, if there are no more questions, I will, going to highlight some of Mr. Kudus' presentations. So in this competing risk, in survival analysis, we can have more than one event. Previously, Professor Al-Fakih talked about one event in survival model analysis. And then here, we can have like more than one event. And Mr. Kudus used tree structure competing risk regression to know the subgroup of the subject. And the application can be in breast cancer and then contraceptive discontinuation. So in the competing risk, the cause of events can be distinguished, such as, for example, the death because of cancer is different from death because of the accidents, and etc. For the discontinuation type, there are failure and abandoning, switching, and censored. Probably later you can see on the material how does this discontinuation types differs. And then For computing risk, Mr. Kudus uses sub-distribution function. And the first application in breast cancers, the treatment are tamoxifen plus breast irradiation and tamoxifen alone. And the event is relapse. And then for the results, we got 4 subgroup of TEM and then 3 subgroup of TEM plus radiation. TEM is tamoxifen. And then for the contraceptive, we have 4 subgroups for the failure event and then 2 subgroups for the abandonment event. And then you can see the conclusions later in the material, okay? Yeah, I think that's all the highlights that I resume for our today's speakers. Alhamdulillah, we are coming to the end of our webinar. Thank you for all the speakers, Professor El-Faqih and Mr. Kudus. And thank you all. And I want to inform you to all the participants, the recording of this Zoom will be posted on Statistika Unisba YouTube channel. And if you want to, access them again and rewatch it, you can rewatch it from the channel. And also for the certificate and today's material will be uploaded in the link which are provided later in the WhatsApp or Telegram and email. So make sure that you do not leave the group to be notified early. And we also wanted to tell you that we will hold another webinar in the topic of dynamic system modeling and simulation on COVID-19 pandemic with experts from Norwegian University of Science and Technology, and also Pajajaran University. So the detailed information will be provided again in the WhatsApp or Telegram group. So thank you for all the participants who are eager to get knowledge from this webinar. I also want to apologize if there are any mistakes in my speech. And at last, thank you all for helping to support the next generation of innovators. We had an excellent event with all of you, and we look forward to see you in the next webinar. Okay, let's close our agenda by reciting Hamdalah. Alhamdulillahirabbil alamin. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you for Islamic University Islamic.
Thank you so much, Dr. El-Faqih.
Thank you for everybody, and wish you have a nice time, and hopefully Jawaba will be released from all of us. Thank you, and for let me be with you in this today presentation, and wish you all the best. Thank you.
Yes,
Okay,
thank you so
welcome,
much.
Prof.
Thank you
Faiz.
for all speakers.
See you. Thank you.
Ya, terima kasih banyak.
Thank you.
Thank you.